Let me take a few minutes to discuss questions 10.27 and 10.31. So first of all, 10.27 was meant to be a really simple question. You were just supposed to find the standard error for the mean. So the sample standard deviation was 9.3, and there are 27 subjects, so you just have to divide by the square root of 27. You'll probably recognize that. That's the formula for the standard deviation of the sampling distribution. Another name for that is the standard error for the mean in this case. So if I divide that out, looks like it's about 1.79-ish. And then part B of the question is just asking you to work backwards. So in part B of the question, you're actually told, you're given this expression in part B. You're told that this represents the mean plus or minus the SEM, the standard error of the mean. So you're trying to work backwards to find the sample standard deviation for these three independent random samples here, these three independent measurements. So literally, I know that's the standard error. So that has to be the sample standard deviation divided by the square root of 3. So all I need to do is take 0.01 times the square root of 3, and I should be good to go. So my sample standard deviation is approximately let's call it 0.017-ish. So that's all there was to question 2.7. And for question 3.1, notice the central limit theorem doesn't apply. The central limit theorem doesn't apply because we don't have a sample size greater than 30. So for these mileage estimates, your first job is to graph them. So for sample sizes that are small, let's say 15 or less, I definitely want to see a symmetric distribution with no outliers. For distributions or for samples that are 15 to 30-ish there, a little skewness is okay. I just don't want extreme skewness, and I don't want to see any outliers. So the bottom line, if I go to plot number 1, I've entered my data into list 1. I can quickly plot a Box-and-Whisker plot and just press zoom 9. And that'll give me a quick graph of the data, which calculates for me that I know there aren't any outliers. And frankly, just by looking at the Box-and-Whisker plot, I can see that the shape is not particularly skewed in either direction. I personally think a better way to look at shape is to consider a histogram. So we can go into that same plot, choose the histogram option, and then zoom 9 it. Again, there isn't anything there that looks crazy skewed in either direction. So I believe for part A, it says to describe the distribution using graphical methods and summarize the results. Well, guys, I have no problem with this. What's most important is the shape. I have no problem if you go ahead and describe all of it. So a complete distribution's description would include the shape, the center, and the spread. So this shape is somewhat symmetric. It has a center at 18.48. The standard deviation is 3.11. You could describe the shape and the center and the spread using those values. That's essentially what's suggested by the answer in the back of the book. But what's really important here is the shape. There aren't any outliers. There isn't any extreme skewness. And that's the answer to part B. That is why it's appropriate to use the methods based on normal distributions. Even though the central limit theorem isn't completely satisfied at a sample size of 20, as long as my sample observations don't show outliers and don't have any extreme skewness, the truth is my sampled means are still approximately distributed normally, and I can still proceed. So using these values, I'm going to write them down in order to do part C of the question. So my sample mean is 18.48. My sample standard deviation, I'll call it 3.12. Those are the values that I needed, so we'll go back so that you can see my work. So I do need to find my critical value. I'm building a 95% confidence interval, so I need to find my critical value. Because I'm using a sample standard deviation, I need to use t-scores instead of z-scores to account for the additional variability. So if you run your INVT program or use the inverse t command, I would enter here for 95% confidence. I'm going to put in not the 0.95, but 0.975. I want to include the 95% plus the 2.5% at the lower end that we've cut off of the distribution, like we talked about. So the degrees of freedom would be 19, one less than the sample size. So this will give me my critical value. It's going to be kind of, oh, it wasn't as slow as I expected, about 2.093. I usually go 3 decimal places on the critical value, but that's more habit than anything else. So to build the confidence interval, I've got my sample mean plus or minus my critical value times the sample standard deviation divided by the square root of the complete sample size. So all I need to do is dump that into my calculator. That is really important right there. You want to show your work that way. The way that I've set it up there, it's important that you're able to set that up and interpret exactly what you see there. So the boundaries that I get, the lower and upper boundaries, on the low end I have, call it 17.02, and on the upper end I have 19.94. So this is the lower boundary I got by subtracting my margin of error. This is the upper boundary I got by adding my margin of error to the 18.48. Now I want to interpret the confidence interval. So we can be, or we are 95% confident, there's the level, that the population mean miles per gallon for this vehicle mean mileage, or miles per gallon, for this vehicle is between 17.02 and 19.94 miles per gallon. So when you interpret a confidence interval, it's important to include the level. It's important to describe what you are trying to capture. I'm trying to capture the true mean mileage for this vehicle, so it needs to be done in context. And then you need to include your lower and upper boundaries also. That's a complete interpretation of that confidence interval. So the confidence level is 95%. To interpret the level, what that tells me is if I build many confidence intervals using this exact method with this exact sample size of 20 over and over again, about 95% of all of those confidence intervals will actually capture the true mean mileage for this vehicle. Okay, so the last part is part E. Do you think that this interval would apply to other similar vehicles? Explain why or why not. And if you read the answer in the back of the question, I think you'd all agree that mileage is dependent on more than just the car and the mechanics of the car. It certainly also is dependent upon the person who happens to be driving it. So I think you'd have a hard time taking this confidence interval, anything that it suggests about the true mean for this vehicle, I think you'd have a hard time in a practical way applying it to other vehicles driven by other people. Hope this has been helpful.